Okay, the first thing today is we're going to continue with the normal distribution, but we're going to move a little bit further than the empirical rule. So the first thing to notice is these z values along the left-hand side here. If you go down to 1, you will see a probability of 0.3413, about half of 68. Plus or minus 1, 68. We go in one direction, we've got 0.3413. So now we're just going to be more exact. If you went down to 24772, about half of 95. Okay. So that's if you have things that come out to be 1.5, which would be 4332. 0.5 would be 0.915. Then after that, the rest of it's just like the empirical rule. You draw the normal curve, shade in the area you're into, get the areas, add, subtract, or whatever. Key being, draw a good picture. But it adds something else, and that is up along the top here. These now are what goes in the 100ths place. So if you calculated a z value, x minus mu over sigma, we'll write that down a few times, and you had the number 1.74, you would go 1.74, and the area for that would be 0.4591. If you ended up with 0.88, you'd go to 0.8, 8 in the hundredths place, 0.3529. Oh, well, I'm sorry, I got in the wrong column. It's up here, 3106. Thank you. Had my 1 circled there. And so 2.51, and the area is 4940. You'll have the table available during the exam, and you should obviously have it available when you do homework. And that's almost the whole lesson today, other than just practicing some problems. And I will add a formula this time, but it's the same concept, the difference between x and the mean in terms of number of standard deviations, the so-called Z formula. And what you'll notice is as we go through the course, much of what we do will follow the same pattern as this. Okay? It might be, instead of x minus mu over sigma, it might be p hat minus p over some measure of standard error, we'll call it then. Or it might be x bar minus mu, the x bar is divided by sigma x bar. But the pattern is going to be the same. Okay, so the first thing is just to kind of read through the problem. We have a normal distribution with a mean of 12.4. This is for the whole population. So mu is equal to 12.4, standard deviation of 0.12, and we want to know the likelihood that we'll get more than 12.5. So I'll draw a bell curve. It will become increasingly important that you label the axis. Tomorrow, it won't be x anymore. So it's going to be different things. And that you put, but again, the pattern is going to be the same. It'll just be different things there. Okay. Z, those numbers on the Z table. Z is the number of standard deviations from the mean. Okay, I wrote something down wrong here. The mean was 12.4. I had it underlined wrong and then just read the wrong thing. The mean was 12.4. Make sure you have that right. Sorry about that. And we want to know more than 12.5. So I'm going to put 12.5 here and shade that in. So the number of standard deviations from the mean. We can see that this distance, I'm going to write it in a formula in a second, but this distance is about 0.1. Okay. That's going to be a little less than one of these. Okay. 0.1 away, it's going to be, I don't know, I think maybe 0.83. We'll calculate it in a minute. Standard deviations away. So Z is just x minus mu, this distance, divided by the standard deviation, or x of 12.5 minus the mean 12.4 over 0.12. And that is 0.83. So now you'll go to your Z table and look up 0.83. Make sure you get 2969. You guys see that all right? 0.83 on your table. That is the area from the mean to this point. So that's the 2969. We know that from the mean up is 0.5. So the area in the tail here will be 0.5 minus 2969. It looks like about 2,031. Yes. Okay. And so that would be your answer on this one. Okay, so on number 2, which is really just a continuation of the same problem, we're still going to have a mean of 12.4 and a population standard deviation of 0.12. But now we want to know between 12.24 and 12.5. Remember, everything has to be done relative to the mean. So I can get this area, which I'll call area A, and I can get this area, which I'll call area B. And since that's 12.5 to 12.4, I already know that one. That one's 2969. We just looked it up a minute ago. So now we need to find area A, and I'll just put Z A x minus mu over sigma 12.24 minus 12.4 over 0.12. And that's 1.33. That's the Z value. That's the number of standard deviations from the mean. Just get this distance, divide by standard deviation to get the number of standard deviations from the mean. 1.33. That goes with 0.4082. And so that's this area on this part of the curve. But we want to go from there to there. So we'll add the 4082, and we'll add the 2969. If my maths okay, that comes out to be 7051. Okay, so the next one again is the same setup. With a population mean of 12.4 and a standard deviation of 0.12. And this time we want to go from 12.5 to 12.6. So I'm interested in that area. So what I have to do is I have to get the whole area from the mean to 12.6. I'm going to call that area A. And then I have to get this area, which I'm going to call area B. And so what you can see is that I'm going to have to take area A from here to here and subtract area B, and that's going to be my answer. Well, we already, again, know area B. We've been using it to 12.5. That's the 2969. So area A, first we'll get the number of standard deviations from the mean, and please do write the formula every time. When I grade this on a test, I'm going to assign some points to the formula. So 12.6 minus 12.4 divided by 0.12. It's about 1.67. That's 1.67 standard deviations from the mean. So in your Z table, 1.67 is 4525. And again, we already have that 2969. And I get 1555. Okay, the next one is a little bit more difficult for most students. It's not that hard, but students do find it a little bit more difficult. We still have the same basic distribution with a mean of 12.4 and a standard deviation of 0.12. But now the question is, find the 90th percentile. Okay? This is like before. Remember, we were doing the 84th percentile or the 16th percentile with the empirical rule. It's the same concept. We're looking for a value such that 0.9 or 90% of values are below this x. Okay, we know that's 0.5. So what we know is the area in this part is 0.4. Okay, that's just the 0.9 minus the 0.5. So now what's going to happen, instead of going along the edges of the Z table and looking up an area, we have to find an area in the center of the table and back our way out to a Z. And we're looking for 0.4. So we go into the center of the table. So we go into the center of the table and find a number that's close to 0.4. The closest number that you're going to find is 0.3997. That's pretty close to 0.4. So you look in the center of the table, and they're in order, so you can work your way into there. And then we find the z value that goes with that. So z is going to equal 1.28. So we have z is equal to 1.28. If you wanted to think about this curve as having another axis, the center of it would always be 0 standard deviations from the mean, and then 1 standard deviation, and then 2. What this says is on this axis, on a z-axis, we are 1.28 standard deviations above the mean. So all we have to do is take the mean and add 1.28 standard deviations. So 12.4 plus 1.28 times 0.12. Okay, so that comes out to be 12.55. So what that means is if this were a test, it's not, but if it were an exam, that's the context where you guys have seen percentiles before, that if that were the score you had, 90% of scores would be below that. So in this case, we're filling this machine with Coke or root beer or whatever. That means that given these parameters, a mean of 12.4 and a standard deviation of 0.12, 90% of the cans would have 12.55 or less. The can really can hold like 13 ounces or something. Okay, so the next one asks for the 85th percentile. So we're looking for, I guess I'll draw that up here. We're looking for a point such that 0.85 are below this point. We know this part's 0.5, therefore this part has to be 0.35. So now I'm looking in the center of the table for a 0.35, and the closest I can get is 3508. We won't interpolate or anything and go between, just get the one that's the closest. If it's exactly in between, we might just say 0.5 at the end of it or whatever. We'll see one in a minute maybe, or at some point. So 0.3508 goes with a z value of 1.04. So the point that we get is going to be 1.04 standard deviations above the mean. Just quickly drawing this out again. '85th percentile. That was 0.35. We're looking for this value of x, and we know that this point has a z of 1.04. So that means that this point is 1.04 standard deviations above the mean. So 85% of values, or 85% of the fill in these cans, is below 12.52. Okay, I'm going to use this same problem, but give you one a little bit different. Instead of finding the 85th percentile, I want to find the 20th percentile. Just to give you the idea of this, this one is, I wouldn't call it tricky, but maybe compared to the other one, a little trickier. So the 20th percentile is right here. We're looking for an x right here. It's below the mean, so whatever we do, we're going to take 12.4 minus some number of standard deviations times, or minus so many standard deviations. Here is the, if it isn't tricky, this is the thing. You don't look up 0.2. From here down is 0.5. So this area, remember we can only go from the mean to some point. This area is 0.3. It's just 0.5 minus 0.2. So now we're just looking in the center of the table for a number that's close to 0.3, and the closest I can see is 0.2995, and that goes with a z of 0.84. So it's below the mean, so we're going to go not quite one standard deviation below the mean. So we're going to have, let's put the symbol, the mean minus 0.84 standard deviations, 12.4 minus 0.84 times 0.12. And that's equal to about 12.3. Okay, so on number 6, we have grenades exploding, and on average, the fuse time is 5 seconds, and we have a standard deviation of 0.25. And we want to know less than 3.5. So I'm going to draw that here. And I'm hoping this doesn't occur very frequently, because it might just take me 3.5 seconds to throw it and get under a rock. So I hope that's a small number. So first I'm going to compute z, x minus mu over sigma is 3.5 minus 5 over 0.25, and that's equal to 6. So that means that this point is going to be 6 standard deviations below the mean, which, remember from the empirical rule, we had 99.7 within 3 standard deviations. So getting 6 standard deviations away is really just not going to happen very often. In fact, if we drew this to scale, that's about 3 standard deviations. 6 standard deviations is down here. So this is an asymptote, which means it never quite gets to 0. There is some probability, but it's going to be very, very low. In fact, I found a thing online to calculate that, and the likelihood would be 9.86 times 10 to the minus 10. So what that would mean is, and you're going to see this kind of answer come up on your calculator from time to time, that e to the minus 10 is just an exponent to the minus 10. So that's going to mean 9 zeros before you get to the well, it's not writing. Well, I'm not having luck getting that done, but the minus 10 means 9 zeros, then the decimal. And it also gives you the odds here. 1 in what is that, a billion? So we've got thousands, millions, billions. So about a 1 in billion chance that you would throw the grenade. And let's say if it takes you 3.5 seconds to get under the rock, that you would, well, it would go off too early and you would be, would not be a good situation for you. So on the next one, I feel a little bit better than this one, more than 5.4. I'm okay if it takes longer than 5 seconds, if that's the average. You know, it just gives me a little bit more time to get under the rock. But the mean is 5. The standard deviation is 0.25. And I want to know greater than 5.4. And shade in the area that you're interested in, so you know whether you need to add or subtract. We can tell on this one that whatever area we get, remember we can only go from the mean to some point, whatever we end up with there, we're going to subtract from 0.5. Z, number of standard deviations from the mean, is 5.4, let me write the formula here, x minus mu over sigma, 5.4 minus 5 over 0.25, 1.6. And then if you look up in your Z table for 1.6, you'll get 0.4452. Again, that's this part, 4552. But we need to subtract that from 5, or 0.5, and we'll get 0.0548. From here, I want to show you one other thing. This is an online calculator. So when you're doing homework or something like that, and in fact, outside of an introductory stat class, if you want to compute Z probabilities, go to this website. There are other websites. This one I think is the easiest one to use. There's a link to it on my website. But we will just go down here and put the mean, which was 5, and we will put the standard deviation, which was 0.25. And we want to know above, so I've got that checked, 5.4, and hit enter. And you'll see it shades the curve in. And down at the bottom here, the probability is 0.0548. For number 8, we're going to be between 4.9 and 5.1. And did you guys get something close to 0.3108 when you tried that one? Good. I wonder if I can write on this one. Nope. I think that's all I'm going to show on that one. You can check your answer on this. What I do want to show you now is they also have value from an area. So up above here we have the mean, which was 5, the standard deviation, which was 0.25, and we want for the getting the first percentile, we want 1%, which is 0.01, and below, if we're looking at the first percentile. So that tells you that you should be getting a number pretty close to 4.418. So, to work this, still draw the curve, mean of 5, standard deviation of 0.25, and we're looking for the first percentile. That area is going to be 0.01. That's 1%, 0.01. That means this is going to be 0.49. And what we need is a z value that goes with that, and then we can compute the x. So if you go into the center of your z table to 0.49, be a little bit lower on this. Go down to 0.49, and the closest I can find is 0.4901. Apparently it's not letting me draw on this anymore. The 4901 goes with 2.33 on the z value. So the z is 2.33. And it's really minus because we're below the mean. But you can just say the mean minus 2.33 standard deviations, and that's 5 minus 2.33 times 0.25. What'd you guys get for that? So about 4.42? Okay. So for homework, it's going to be the stuff that's on here, and I'm going to post one more problem with several parts on it, so we can get plenty of practice on everything. Okay. Tomorrow we're going to do something called the central limit theorem. And I only know of two theorems in statistics. This one and something called Cochrane's theorem. Not our Cochrane that works up here, someone else. But it's the cornerstone of inferential statistics. Yes? Yeah. That's okay. I'd like for them to know too. So anyway, it's the cornerstone of statistical inference, and so it's going to be, I think, really important for you to understand that. It's not so much that we're going to use it every day, but we're going to use the understanding of it every day.